Hey, you ever look up at the moon, just hanging there and think, yeah, gravity. Makes sense. Apple fell. Moon orbits.
Mm-hmm.
Okay, let's unpack that makes sense part because, well, the rabbit hole of gravity goes way, way deeper than that.
Oh, absolutely. Much deeper.
We're about to take a glorious plunge into some seriously mind-bending ideas, all thanks to this uh, beast of a book, An Introduction to General Relativity and Cosmology.
It's definitely a thorough text.
Now, don't let the title scare you.
Yeah.
Think of it as our treasure map today, guiding us to some of the most, well, bizarre and beautiful secrets the universe has to offer.
But without getting totally bogged down in the math.
Exactly, without getting lost in a jungle of equations, our mission to wrestle with some of Einstein's wildest insights about gravity, space, and time, the stuff that really makes you go, huh.
In the best possible way.
In the best possible way. Get ready for a cosmic rethink.
You know, it's fascinating how even the giants, like Newton, have their almost got it moments. He gave us this incredible framework. I mean, it worked brilliantly for so long. But as our observations got better,
The cracks started showing.
little cracks, yeah. Hints that something was missing.
You'd think a planet, on its own, would just trace this perfect ellipse. Like clockwork.
That's the simple picture.
Right.
But astronomers noticed these tiny wobbles, these shifts.
Like with Mercury, wasn't that the big one?
Mercury was key. Being so close to the sun, the effect was more noticeable. It's perihelion, the closest point to the sun in its orbit.
Yeah.
It wasn't staying put. It was slowly rotating.
Slowly being the operative word, right? Like super slow.
Oh, incredibly slow. Maybe 1 or 2 arcseconds per century. Tiny.
Sounds like nothing, a cosmic hair's breadth.
But it was real and measurable.
Mm-hmm.
Enough to make scientists think, maybe gravity isn't quite this simple.
Maybe there's more to it.
Exactly. These subtle discrepancies, they were like the universe whispering that Newton's theory, while amazing, wasn't the final word.
Because he had simplifying assumptions, right?
Yeah.
Spherical sun, empty space.
Precisely. And the real universe is messier, more nuanced. Even tiny deviations add up over cosmic timescales.
Okay, so Newton laid the groundwork, fantastic foundation, but we needed an upgrade. Enter Einstein.
And his general relativity.
Now, digging into GR, we immediately hit these things called tensors. Powerful, apparently, but also kind of abstract. What are they?
Well, fundamentally, they're mathematical objects that go beyond just numbers, like temperature or arrows with direction, like wind.
Okay, so not just scalars or vectors, more complex.
Yeah, they capture relationships that might depend on multiple directions or how things change between different viewpoints. Crucially, they let us describe things like space-time curvature in a way that works no matter what coordinates you choose.
Ah, so they're like this universal language for geometry. It doesn't matter if your map is upside down, the tensor description holds.
That's a great way to think about it. Coordinate independence is key. Now, there are rules.
Always rules.
Slight chuckle. Always rules. For instance, with a specific type, a mixed tensor, it has both upstairs and downstairs indices, you could say.
Okay.
If you do an operation called taking the trace, basically summing over paired indices, you get a scalar, a simple number.
And that number is real, like objective. It doesn't change if I switch my coordinates.
Exactly. It's an invariant, a little piece of absolute truth hidden in the complexity.
Cool. But you also said we can't just add up any random tensor bits.
That's a really important point in curved spaces. If you just grab, say, all the contravariant components, the upstairs ones, and add them,
Yeah.
the result usually won't transform nicely. It won't act like a proper tensor when you change coordinates. It becomes coordinate dependent.
So it's only meaningful in one specific view.
Pretty much. There are exceptions in simple cases, but generally you need specific operations like the trace to combine components and still get something tensorial, something coordinate independent.
Okay, tensors have rules.
Got it.
Then there are tensor densities. What makes them denser?
It's about how they transform. They're very similar to tensors, but when you change coordinates, they get an extra factor multiplied in.
An extra factor.
Yeah, related to something called the Jacobian of the transformation. Remember that from calculus?
Vaguely. Tells you how volumes or areas scale when you change variables, right?
Exactly. So a tensor density picks up a factor of the Jacobian raised to some power called its weight. It's sensitive not just to the coordinate change itself, but how that change stretches or squishes space.
Whoa. So they know about the distortion, too.
Yeah, in a sense, yes. A scalar density, the simplest type, just gets multiplied by the Jacobian to its weight W. It carries this extra info about the volume element.
And they only work for nice, non-weird transformations.
Generally, yes, defined for non-singular transformations where the Jacobian isn't zero. It's a subtle point. The book gives an example, actually, of a combination that transforms as a density with weight minus 1.
Okay, intricate tools. Tensors, tensor densities. How do they help with gravity? The book mentions geodesics. Straight paths in curved spacetime. That sounds wrong.
It does sound like an oxymoron, doesn't it? But it's fundamental. In flat space, a straight line is the shortest path. Geodesics are the generalization for curved spaces, like Einstein's spacetime.
It's like flying the shortest route on Earth. That's a curve on a flat map, but it's straight on the globe.
Exactly. A great circle route. Geodesics are the spacetime version of that. They're the straightest possible paths objects naturally follow in curved spacetime.
So, wait. A planet orbiting a star. It's not being pulled, it's just going straight, but space-time itself is bent.
That's the revolutionary insight. It's following its geodesic. The path looks curved to us because the space-time stage is warped by the star's mass and energy.
Mind blown. Okay, and there's an equation for this, the geodesic equation.
There is. It involves derivatives and these things called Christoffel symbols.
Yes, the Greek letter soup I saw.
Slight chuckle. It looks daunting. But the key is, in flat space-time with simple coordinates, those Christoffel symbols are zero.
And the equation just says?
Basically, acceleration is zero. Constant velocity, straight line. Just what Newton would say in empty space.
But in curved space-time, the symbols are not zero.
Right. And they dictate how that straight path actually bends relative to our coordinates.
And the time for an object following this path is its own personal time, proper time.
For massive particles, yes. Proper time is the natural parameter along its world line. It's geodesic.
Okay, straight paths that look curved. What if you have two nearby paths, like two particles starting side by side? Do they stay parallel?
That leads to geodesic deviation. It asks exactly that. Do nearby geodesics diverge, converge, or stay parallel?
And flat space.
In flat, torsion-free space, using Cartesian coordinates, the equation is simple. They either stay parallel, or drift apart, or together at a constant speed, like parallel laser beams in a vacuum.
Makes sense, but in curved space.
Much more complex. Curvature itself can pull initially parallel paths together or push them apart. Think tidal forces. If there's torsion, this sort of twisting of space-time, that adds another layer.
So finding out how they deviate is hard.
Often very hard. You might need numerical simulations or approximation methods. Gravity doesn't just bend paths. It affects how bundles of paths evolve relative to each other.
Like tidal forces stretching things?
Precisely. Which neatly brings us to the Weyl tensor.
Okay, another tensor. What's special about Weyl?
It's a specific piece of the bigger Riemann curvature tensor, the one that holds all the curvature info. The Weyl part is often called the trace-free part.
Trace-free. What does that mean for space-time shape?
Think of it like this. Part of the Riemann tensor tells you how volumes change because of matter and energy that involves a trace operation. The Weyl tensor is what's left. It's the part that distorts shapes without changing volume. The pure stretching and squeezing. The tidal part.
So Riemann has volume change and shape change, and Weyl is just the shape change part.
Yeah, it's a good way to picture it. And there's a key theorem. If the Weyl tensor is zero in a space with n dimensions, then that space is conformally flat.
Conformally flat sounds stretchy.
It means you can basically take the metric, the geometry description, and multiply it by some scaling factor everywhere, and boom, you get the metric of flat spacetime, Minkowski space.
So it's like a distorted version of flat space that you can theoretically undistort just by stretching or shrinking it the right way?
That's the idea. It's like
Yeah.
uncrumbling a sheet of paper perfectly,
Yeah.
but there's a catch.
Of course there is.
In 3 dimensions and 3, the wild tensor is always 0, but that doesn't automatically mean it's conformally flat. You need another thing, the Cotton-York tensor, to be 0 too.
Why only 3 dimensions?
It's just one of those mathematical quirks of geometry. And weirder still, in 2 dimensions, every metric is conformally flat. Dimensions matter.
The universe likes its exceptions. Okay, shifting slightly. Killing vector fields sounds ominous.
The name is a bit traumatic, yes.
Yeah.
They're named after Wilhelm Killing. They represent symmetries of space-time.
Symmetries, like if you move or rotate things and it looks the same.
Exactly. A Killing vector field points in a direction along which the metric, the way we measure distances and times, doesn't change. Think of a perfect cylinder. Slide along its axis, it looks identical. That direction corresponds to a Killing field.
So it generates an isometry, a symmetry transformation.
Precisely. And these aren't just abstract. They're deeply connected to conservation laws. Time translation symmetry, energy conservation, spatial translation, momentum conservation, rotation symmetry, angular momentum conservation.
Wow. Geometry equals physics laws.
It's profound, and there's a limit. An n-dimensional space can have at most n plus 1, 2 independent Killing fields, so a maximum amount of symmetry.
And they have structure.
Yes, if you combine 2 Killing fields mathematically using something called a commutator, you get another Killing field. They form a structure called a Lie algebra. The symmetries are organized.
Okay, so space-time has geometry, it has symmetries.
Yeah.
This all leads to the Einstein equations, right? How did he connect geometry to gravity?
His genius started with the principle of equivalence. Gravity feels just like acceleration.
Right, the elevator thought experiment.
That led him to think that in a gravitational field, the metric tensor, describing the geometry, must have components that change from place to place. Space-time isn't flat.
Because the fabric is warped by mass.
Exactly. And crucially, unlike the accelerating elevator where you can find coordinates where things look normal locally, in a real gravitational field, you can't get rid of the curvature everywhere just by changing coordinates. It's intrinsic.
Gravity is the curvature, not a force pulling through flat space.
That's the leap. And remarkably, the mathematician David Hilbert got to the same equations independently from a more axiomatic approach.
Shows the idea was solid.
Very. At the heart of the equations is the idea that matter and energy described by the energy-momentum tensor tell spacetime how to curve, and spacetime curvature tells matter how to move.
It's a dialogue. Matter sculpts spacetime, spacetime guides matter.
Beautifully put. The equations themselves, R12 gain plus ATET, they link the geometry, left side, to the matter-energy content, right side.
Okay, so those equations are the rule book. What happens when you apply them to the whole universe? Cosmology. FLRW metric.
Right. On the largest scales, we assume the universe is pretty much the same everywhere, homogeneous, and looks the same in all directions, isotropic, the cosmological principle.
Big assumptions, but they seem to work.
On large enough scales, yes. Given those symmetries, the most general metric is the Friedmann-Lemaître-Robertson-Walker metric, FLRW for short.
Easier to say.
Much. It describes an expanding or contracting universe. It has a scale factor, RT.
Which tells you how big space is getting.
Essentially, how distances between galaxies stretch over time t. And it has a curvature parameter, k.
K tells you if space is flat or curved like a sphere or like a saddle.
So offer k0, positively curved, k plus 1, or negatively curved, k1. Friedmann and Lemaitre found solutions using this metric, showing how RT evolves depending on what kind of stuff fills the universe.
And this expansion explains redshift.
Yes. As the universe expands, Light waves traveling through it get stretched. Longer wavelength means redder light. The amount of redshift, Z, tells you how much the universe has expanded since the light was emitted.
The 1 plus Z equals R now rough in a formula.
That's the one. And for nearby galaxies, this leads directly to Hubble's law. Redshift is proportional to distance,
V equals H euro. The farther away, the faster it recedes.
with H here, the Hubble parameter, telling us the current expansion rate.
Okay, expanding universe, check. But then the horizon problem. What's the issue with the horizon?
It comes from looking at the cosmic microwave background, the CMB, the oldest light we see.
The afterglow of the Big Bang.
Right. And it's incredibly uniform in temperature across the entire sky, to like 1 part in 100,000.
Which suggests those different parts were connected, right, in thermal equilibrium.
That's what thermal equilibrium implies, yes.
Yeah.
They must have been able to exchange energy, to talk to each other, to agree at a temperature. But back when the CMB was emitted, about 380,000 years after the Big Bang, according to the standard model without inflation, regions on opposite sides of the sky we see today were too far apart for light to have traveled between them since the very beginning.
They were outside each other's causal horizon. They couldn't have communicated.
Exactly. So how did they end up at the same temperature? It's like finding 2 perfectly matching ice cubes miles apart in a desert. How do they coordinate?
That is a problem. It seems impossible.
It's a major puzzle for the standard Big Bang model, which leads us to
Inflation, the proposed fix.
the leading idea, yes. Inflation proposes a period of incredibly rapid, accelerated expansion very, very early on, like the first tiny fraction of a second.
Way faster than the expansion now.
Exponentially faster. The idea is that it took a tiny, causally connected patch of the very early universe.
Where everything could talk and reach the same temperature.
Right. And blew it up to enormous size, vastly larger than the region we can observe today.
So the uniform region we see was connected before inflation stretched it all out.
That's the core concept. Inflation solves the horizon problem by ensuring the observable universe originated from a small, smooth patch.
What drives that crazy expansion?
It requires something with a very strange equation of state, typically described as having negative pressure. Roughly, Peter's man.
Negative pressure, like anti-gravity.
It acts that way, driving repulsion and accelerated expansion. It's still theoretical, but it solves several cosmological puzzles.
Okay, from the ultra-early universe to the ultra-extreme black holes. The Kerr metric for rotating ones. More complex than the basic Schwarzschild.
Oh, definitely. Schwarzschild is just mass. Kerr involves mass and spin, angular momentum. Rotation twists space-time around it.
Twists space-time? How does that work?
It's called frame dragging. The metric is more complicated. The book notes it didn't have a simple invariant definition initially, making its discovery quite a feat. But in certain coordinates, like border Lindquist, you see the rotational symmetry. The metric doesn't depend on the angle around the rotation axis.
Like spinning a top, it looks the same as it turns.
That kind of symmetry, yes. And if you set the spin to 0 in Kerr, you just get back Schwarzschild.
What new features does the spin add?
The big one is the ergosphere, a region outside the event horizon where space-time is dragged around so fast you have to rotate with it. You can't stand still relative to distant stars.
Whoa, forced rotation.
And the event horizon itself changes.
Yes, its shape and size depend on the spin. And this leads to the possibility of naked singularities.
Naked singularities. That sounds bad.
It means a singularity without an event horizon hiding it. In the Kerr metric, this happens mathematically if the spin parameter A is large relative to the mass m, specifically if m in the right units.
So if it spins too fast, the cloak comes off.
Mathematically, yes.
Okay.
The equations don't predict a horizon. This is problematic because it might mean information could escape the singularity, potentially violating causality.
Could we see one? Interact with it?
That's the scary part for physics. But the cosmic censorship hypothesis suggests this probably doesn't happen in reality.
Nature prevents it. The idea is that collapsing stars, likely shed enough angular momentum so they always form a horizon. Naked singularities are generally thought to be astrophysically unlikely, even if they're mathematical possibilities.
Okay, that's slightly reassuring. But then you mentioned the sun and Earth technically have a fin. How can that be?
It's true, but it's a bit of a mathematical quirk. For objects like planets or stars, their physical size is vastly larger than where the singularity effects would become important. They aren't collapsed down to that point. So while the condition is met, the extreme phenomena horizons, singularities only apply when you have that incredible density, like in a black hole. It doesn't mean the sun is about to become a naked singularity.
Okay, context is key. Phew. Wow. So from those tiny planetary wobbles Newton couldn't quite explain,
To the twisting space-time around rotating black holes.
it's just an incredible journey. General relativity really did rewrite the rules of gravity, space, and time.
Completely. We've gone from Newton's limits through tensors, geodesics, the details of curvature with Whale, the importance of symmetries with killing fields,
The Einstein equations themselves, the expanding universe, the FLRW metric, the horizon puzzle, inflation.
and finally, the complexities of curved black holes. It's a rich tapestry.
It really makes you see the universe not just as stuff moving in a fixed arena, but as the arena itself being alive, dynamic, shaped by the stuff within it.
That's the essence of it. And even this dive, it's really just scratching the surface. There's so much more depth.
So maybe the next time you look up, that feeling of normal gravity might feel a bit different. Think about it. How does living in a universe where space and time are curved, where straight lines aren't always straight, change how you see reality? What other bizarre truths are still out there, waiting at the edge of what we know? Makes you wonder, doesn't it?